Myself and one of my agronomists at the time discovered this ratio that people use all over the globe, and it's called the magnesium to potassium ratio. And how we discovered it was we noticed that if you could get, because we're looking at soil tests and leaf tests and comparing them and doing some research we were doing at the point with all the stuff we had in our data bank, we noticed that if you can get equal parts per million on your soil test, so here it would be like 400 or something of each, then what happens is you've got maximum uptake of magnesium and maximum uptake of potassium, but a strange other thing happens. On the leaf test, in pours the phosphorus, and you're thinking, how's that working? Well, here's how it works. These two minerals are super antagonistic of each other. High potassium shuts down magnesium, high magnesium shuts down potassium very, very strongly. So you got them just where they need to be, which is equal parts per million, and you've got nothing stopping potassium, nothing stopping magnesium until they pour in. And then you say, well, what about phosphorus? Why does phosphorus suddenly go into the plant? Well, you know, sometimes more than putting phosphorus on there, because magnesium is a phosphorus synergist. Just like boron pushes calcium in, magnesium pushes phosphorus in. When you've got the right amount, in comes the phosphorus, and potassium antagonizes phosphate. So if you've got too much, it stops phosphate going in, so you've got the perfect amount, equal parts per million, and then pours the phosphate. It's a hell of a finding. It's really been valuable for people, and we discovered it, so that's my other great claim to fame, I guess. So here you say, okay, how's this bloke doing? Well, he's called me and said, look, I can't even sell my grapes. They're so sour, and they're tiny, tiny little grapes. What the hell's going on? Well, here's what's going on. That's what he needs, minimum 400, and what he's got is 114. He's got no potassium on base saturation. You need 5% to 6% for grapes. He's got 0.85%. He's got this screaming neglect of potassium in his program. And he's got high magnesium as well, so magnesium shuts down potassium, so you haven't got any to start off with, and what does it do? It sizes things up and sweetens things. It pumps sugars to size things up and sweeten them. You've got sour, tiny grapes that you can't sell because you've got no potassium. His first role, immediately, normally we say fix calcium first. No, in this soil you wouldn't, because the guy has to make some money. First thing you're going to do, get some potassium. Just foliar spray. 8-10 kilos of potassium sulfate with some fulvic acid, and get potassium into that plant to get the ball rolling so you can make some money, is what we'd be suggesting here. You can't really afford to fix this thing in the soil, because this is 300, when you do the sums, it's 300 kilos per acre of potassium. Potassium sulfate's half, it's about 800 kilos of pot sulfate, and pot sulfate's $1.70 a kilo, so it's going to cost you $1,200 to fix this thing. And he hasn't got $1,200 because he's struggling at the moment because he can't sell his grapes. So we've got to look at putting that into the leaf and so forth because of that. Phosphorus to sulfur ratio, what's that about? Well, it's a really important ratio because phosphorus, if you've got too much of it, shuts down sulfur, and too much sulfur shuts down phosphorus. They're super antagonistic anions, and what you want is equal parts per million. So if you had your 50 here, you want your 50 of sulfur. Well, he almost got that because he's got the humus that holds the sulfur. He's got 43. But this guy needs to do his phosphorus here. But at 1-to-1, you've got best uptake of both those very important minerals. Remember sulfur, how important it is, and you're all neglecting it, how important it is. Everything that determines resilience, every compound is sulfur-based. If you want resilience in the face of more and more extremes, you've got to do sulfur. You've got to have that capacity to fight the fight against all these abiotic and biotic, which means environmental and pest and disease pressures. Sulfur is just so important, it's crazy. You can't make protein that drives immunity without sulfur, because the two amino acids that make protein, there's many, but the two most important are called cysteine and methionine. They're made from sulfur. You can't make proper sulfur and have proper immunity. So you can't make proper protein and have proper immunity without sulfur. So so phosphorus to sulfur ratio 1-to-1. Well, all he needs to do here is build his phosphorus. He doesn't need to touch sulfur. He's almost there. Phosphate to zinc ratio, another phosphate. So this one here, the magnesium to potassium, equal parts per million, pushes in phosphate. Phosphate sulfur determines, if you've got them 1-to-1, you've got best phosphate. There's another phosphate one, phosphate to zinc. So this is quite important because what you're chasing, the ideal ratio is 10 parts phosphorus to 1 part zinc. So we say, well, how's this bloke doing? Well, he's got a deficiency of phosphorus, 23, and he's got a deficiency, but wait a minute, 10 times 2.3, he's got a 10-to-1 ratio. He fluked the perfect rate, even though he's really deficient. And now he says, well, I can't afford to put the 400 or 500 kilos of guano that I need to fix my phosphate, but I can put my 22 kilos we worked out of zinc sulfate on here, because that's just going to cost me $30. So I'll do that. Worst thing you could ever do. You never, ever, the ratio is more important than the numbers game. So what you do if you've got a limited budget, which most people do have, you say, I'll put a little bit of phosphate and lift this up to 30, and I'll put a little bit of zinc and lift this up to 3, but you maintain, because what he's got is the perfect uptake of those two minerals despite his deficiencies. And if he puts the zinc on and doesn't change phosphate, he hasn't got the 10-to-1 anymore, zinc will shut down phosphate. So suddenly he's got a induced phosphate deficiency, seeing these purple lower leads that weren't there before because you were just getting through because you had the perfect ratio. So if you're fixing it, you fix them together with your budget, lift it to 30, lift zinc to 3. It's just a few kilos of zinc, and you can work out how much that is to lift it to 3. This is all on the app in much more detail, so you can go back to it and refer, and you know then how to read your soil test and how to program your soil. It's on the new app. So phosphate to zinc 10-to-1, fix them in conjunction with each other, step by step as you can afford it, but the ratio is more important than playing the numbers game. It's the best ratio for the uptake of both minerals. The sodium to potassium ratio, this is the only other time that we come down to this. The Cal-Mag ratio is on this base saturation, the saturation of the bases on the clay colloid. The key cations are called bases, and their saturation, their percentage that they're stuck onto that clay. The only other time we go down to, here's the really important thing. You look at your soil test when you get home, because you never want to see this. You never want to see what you see here. Here's the story. We talked about plants determining what they want based on the size of the ion. It's called ionic radius. The big beach ball is calcium, the small golf ball is magnesium. Potassium and sodium are identical, are exactly the same size. And what the plants evolved to do since the start of time, these two things, the one that there's most of is always potassium, because that's how it always was until we stepped in. Whatever there's most of, and those identical things on the clay, when you sense it, however you do that, you take the one that there's most of, always. And that's what this plant's doing. Because when we look here, we see he's got more sodium. He's got 0.85%, and he's got 1.31. He's got more sodium. The plant's desperately wanting potassium, and has seen this thing where there's more sodium, and it's taking sodium. He said, I've got all these burnt leaves for sodium. Why? 1.31 doesn't do that. Yeah, it does if you don't have potassium, and your plant's screaming for it. It thinks it's taking potassium. It's taking the one there's most of. And his first job here is to put enough in here so that it's higher than sodium, so the plant will actually at least take it rather than sodium, because it can't differentiate, because the natural scheme of things there's always more potassium than sodium, but we pulled out the trees and lifted the salt, used salt fertilizers, hated on irrigation water, and changed the whole scenario, and the plant hasn't caught up with our mismanagement. It still uses the same thing it always used, which two things, the one there's most of is going to be potassium. So you never want more sodium stuck on the high percentage on base saturation of sodium, because you will be uptaking sodium instead of the money mineral, and that's going to cost you. And if you have got high sodium and you can't fix that, you can't make it more, you can't afford to, you've got 7% sodium and you've got 2% potassium, and you can't change that, then you foliar spray potassium and make sure the plant's got the money mineral that's going to make you your profit. That's how it works. Iron to manganese is, we go here and have a look, this is back to the parts per million. We want, here we can see the ideals, never more than 2-to-1, 200 to 100 with high manganese soils, but 40 to 30, just a bit more, it's 1.3 to 1. It's always a little more iron than manganese. So how's this guy doing? Well, he's got 283 parts per million iron, he's got 28, that's a 10-to-1 ratio. He's manganese deficient. And that's going to give you stripes called endoveinal chlorosis. That's going to mean you're lacking sugar factories. So you're going to foliar spray manganese, and that's just a kilo of manganese sulfate with some fulvic acid, $3, and that you fix that particular problem for that season. So yeah, so that you look at that ratio, and if you've got this ridiculously high iron, then iron affects manganese first, and then it also affects zinc as well. So yeah, the high iron's quite an issue here that you need to fix. So that's just that concept, and you've got notes that you'll be receiving that covers that story that you've just heard. We've talked about cation exchange, so I'll just see if there's any other things that we need to talk about. We use the lab at Southern Cross University in Lismore. They do the whole balancing Albrecht story, and then we just run it through to that soil therapy format, which gives you all the guidelines and all that sort of thing. So what you will do on the app is that you just put your soil test figures in there, and it will convert that to a soil therapy chart with all the guidelines and everything. So it's just a bit of a helpful thing. We've covered most things about phosphorus, the fact that you only get 27% of what you put out before it ties up. So if you've got an orchard or you've got a grazing property, then there's not much sense in using water-soluble phosphate. You're far better off using a natural phosphate or chicken manure source for that. And that's just talking about, well, let's talk about how you can release. So if you do your total, even if you just do total P, which is, like $20 extra on a soil test, which is how much have I got locked up? And if you've ever used phosphate, you've got a lot locked up. If you've never used phosphate, you might have natural phosphate that's in soluble form, or you might have nothing much, which means you've got to do some work with phosphate. But most people have got lots of it. I mean, I've been working on red soils with these very large-scale potato growers in Victoria. They're putting on 2 tons of NPK fertiliser at starter, which is phosphate-dominated, and as soon as the leaf comes out of the ground, they send it off and get a leaf test, and they're out of phosphate. I said to them, have you done a total? No. You've got red soils that's got, iron has 3 positives, phosphate's got 3 negatives. It's just filled with iron. That's what makes it red. It's iron oxide. And boom, those 3 grab the 3 negatives and you locked it up, and that happens in 3 weeks, which is exactly the time when they do their leaf test. I said, you're going to have massive. They had truckloads equivalent of DAP tied up in their soils. And I said, what you need to do is save yourself a fortune and use some of the strategies that will release that phosphorus. And that's what they do. And they've had some of their record yields ever in the last year. So what sort of things can you do? Well, compost, of course, contains a hothouse of biological activity that can go to work. Many of those organisms, many fungi can solubilize locked up phosphate. Many phosphate solubilizing bacteria, which are in compost, can help with the release of phosphate locked up in your soil. Legumes, functioning legumes that have nodules and have red inside them, release an acid that breaks, just like you take rock phosphate, it's insoluble, but it slowly releases. And you say, no, I want it immediate, I want fast food. And so you put sulfuric acid and that makes super, or you put phosphoric acid, you break them apart and you've got soluble phosphate. But you didn't change the nature of the beast, and so as soon as it gets in the soil, it just starts looking for positive things to join up with, and then it becomes insoluble again. In fact, it becomes usually the same material it started with. It becomes calcium phosphate, which is insoluble. So legumes do it gently. They're releasing this acid constantly. Remember, if they're functioning, they're releasing this hydrogen-based acid, and that trickle feeds, breaks apart the tied up calcium and phosphorus in your soil. Fulvic acid is very well researched to release phosphorus. Mycorrhizal fungi, wonderful. They actually, the main reason the plant feeds this little parasite, well, you could think of it as that, but it gives more than it takes, but it joins on the roots, spreads out, gives us 10 times the original root surface area. And the main reason the plant's looking after it is because it will go and get those very immobile minerals and bring them back to the plant. So it will grab phosphate, which doesn't float around in soil solution, it sits where you put it, and zinc is the 2 most immobile minerals. Mycorrhizal fungi is wonderful for going out and accessing those. Plus, it also releases acids that these natural acids from that big hyphal network that release locked up phosphate, break apart phosphate and calcium. And stubble digestion can be very good, particularly if you're using something like trichoderma, which also releases phosphate. BAM releases phosphate. So there's a bunch of things you can use to untie your locked up phosphate. We talked about magnesium, and we talked about the things that antagonize it, and that's just some of the things that magnesium interacts with. I won't spend too much time because that's just talking about forms of magnesium. A really good form, if you don't need calcium but you need a heap of magnesium, there's 2 mines in Australia with something called magnesium carbonate. You can see it's got 27% versus 10% in dolomite. And magnesium oxide is a bit hot, but it's half magnesium, so that's handy. Now, magnesium sulfate, people say, oh, I've got a magnesium deficient, I'll just put out some Epsom salts. No, you never do that. Why? Because that's how you get rid of magnesium. You put gypsum in there, it forms magnesium sulfate, and magnesium sulfate leaches like a mad dog. So you don't ever try and correct something with something that leaches. That's why you use magnesium carbonate or dolomite, or if you need calcium, you use dolomite, but never magnesium sulfate. Now, there is a role for magnesium sulfate. It's wonderful. You foliar spray it if you're magnesium deficient. You use amounts like 5 kilos per hectare is my favourite. A lot of people use less, but 5 works and it doesn't burn. Put a bit of fulvic acid and you fix your magnesium through the leaf. There's also, again, you can micronize magnesite and you get your 27 or slightly less. It's 20.5%, and it's just instantly available. So fine, it's only 5 microns. That's the micronized mineral suspensions that I talked about. Potassium, we've talked about the supermobile mineral. See, the problem with potassium, and it's why of all the meters, and we'll talk about the meters later, it's probably the most important meter is a potassium meter. Why? Because it really determines your profit, and that's what you've got to make money. And the more the better to be viable, particularly when you've got bad seasons and good seasons, you've got to counter them. So potassium basically is the most mobile of all minerals, nitrogen second. It's the second most abundant mineral, so it's really important, but it's the most mobile. So it rushes from if you run out of the grain tips or you're sizing grapes or sizing grain or whatever, and you run out of potassium, and you're measuring with a normal leaf test, the first fully developed leaf, I'll teach you how to do that later, you're measuring where it's moved to, and you don't even, by the time the entire plant's drained and you measure that top leaf or that leaf 3 leaf, 4 leaves down, you say, oh, you've been potassium deficient for 6 weeks. You're not going to catch up. You lost yield. The money mineral wasn't there. So this is why it's these new leaf tests or the meters, you measure top leaf, bottom leaf. You measure that first fully developed leaf and then you measure it, and they need to be the same. And as soon as there's 10% less on a meter, then so you put a few little drops on one end, and then you put the bottom up from the top, and then you take the bottom leaf, squeeze it, and put 3 little drops, drip, 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 with your garlic crusher on the bottom, and then you look at your chart. And if it's acidic, it will be darker. If it's more alkaline, it'll be lighter. It needs to be the same shade at both ends of that strip. And if it's darker at the bottom leaf, that is almost always a potassium shortage, because potassium is what alkalizes, and you're measuring pH. There's the pH strip. You're measuring pH, and if you're lacking potassium, the most alkalizing mineral, then you're going to be acidic on that bottom leaf. And then you're going to have disease. Where does it come? The bottom leaf. Always, that's where it starts to be based on exactly that principle. So that's a simple little hack you can use in the home garden. Drop on one end, drop on the other. They've got to be the same color. If it's darker on the bottom one, you need potassium. It's a simple little strip technique. Now, potassium sulfate is not usually used. I mean, we have fancy potassium things like K-Ridge, but honestly, the cheapest thing for you is potassium sulfate, because mostly you need sulfur anyway. And people say, oh, yeah, but it doesn't dissolve. Yeah, it does. It's 1 kilo per 10 litres. So if you're using 100 litres in broadacre, you use 8 kilos, and that dissolves beautifully, and that gives you a hell of a potassium hit, particularly if you put some fulvic acid with it. So it's actually a really good foliar because it's taking care of your sulfur, which is almost everyone needs more sulfur at the same time. So in orchards, you might go a little high because you're using much higher water rates. You might go 10, 15 kilos as a foliar. It doesn't burn because it's buffered. The sulfur buffers the burning effect of potassium. It's actually a really good foliar. Sulfur, I could never understand. We talked about sulfur. We used to get it for free because it went up as sulfur dioxide from industry, and it came down as acid rain. So we got some sulfur for, and then we banned that, so that doesn't happen anymore. You're not getting it for free. But what I could never understand is that you could look at a soil test and say, okay, we need some sulfur and we need calcium, so we'll put this much gypsum in. Or we could put elemental sulfur, which has got way more sulfur in it than gypsum. Gypsum's only got 15%, elemental sulfur's like 95% sulfur. It's the yellow granules. But why is it? I mean, one of them's plant available. The elemental sulfur's got to be broken down by bacillus organisms to convert it into the plant available sulfate form. And that takes a week or 2 or 3 or 4 weeks, depending on what your soil's got in it. But why is it that you can take a paddock and you can put out yellow and you put out the same amount of sulfur in the form of gypsum, and the sulfur, the elemental sulfur, just can paint that paddock green like you put urea out there? How the hell is that? I couldn't understand for years. Why is that happening? How is that possible? And then I understood that these little mouths called stomates, these little breathing mouths, which you're aiming for when you foliar spray on the underside of the leaf, you want something that can fluff up the leaf. That's why drones are really effective, because they've got that, they're flying quite close and they're flicking the leaves and they're getting on both sides for foliar spraying. But that little mouth, it turns out during the conversion of this stuff, when these organisms start changing it into sulfate form, the plant available form, some of it goes up as gas. And this little mouth says, yeah, thank you, and sucks up the gas. It doesn't just suck up CO2 for photosynthesis, it also can take sulfur gas. Sulfur as a gas cycle. So it sucks up that sulfur, and that paints your paddock green. So I love elemental sulfur. It's a really, really good option. It's a wonderful option. It gives such a nice response. And that's just talking about sulfur relative to all the things that it does. The 2 amino acids that are sulfur-based, the nitrogenase enzyme and the nitrate reductase enzyme, we talked about their molybdenum role was close second to sulfur. So you're not having either of those fixation or the conversion of nitrates to protein without sulfur. So it's pretty important. Nodules, if you haven't got nodules on your legumes, you're lacking sulfur. And it's so many other things it does, including transport of sugars, down to the roots from the leaf where the sugar's made. So your soil life suffering if you're sulfur deficient because you're not getting enough sugar translocated down there. Then we talk about it's linked to disease, and we see all these different diseases that are linked to a lack of sulfur. Published studies on downy, verticillium wilt, fusarium, phytophthora, rhizoctonia, sclerotinia, alternaria, and various rust and blight diseases linked to the lack of sulfur. And I'm saying pasture dieback is linked to, we'll see if I'm right, but that's my theory, is linked to a lack of sulfur. So really important. Silica, we talked about how it works. It's about strengthening that cell wall and that it's also an immunoliciter. But when we talk about silica, it's not just strengthening the cell wall. I mean, phloem and xylem are the pathways that move things in and around, including water, in and around the plant. They're made from silica. So obviously it's a fairly important. Why wasn't it made essential mineral? Now we're going to, but it wasn't for all of these decades ever considered an essential nutrient. But your transport of moisture and nutrients around the plant is based on pathways that are made called phloem and xylem, made from silica. I mean, you can see the silica is an important neglected concept. Boron, we've talked about how important it is. Interestingly, you can use a refractometer. I'll cover that when I talk refractometers. Zinc, probably the biggest cost to benefit ratio. If you're zinc deficient, you're going to have a smaller leaf because zinc is needed to produce auxins that govern leaf size. So any kind of deficiency means smaller solar panel, less production. So it can be very costly, a zinc deficiency. So look at this study of molybdenum. This is a very famous New Zealand study conducted by a bloke called Professor Lobb from the university in Lincoln University in the South Island. We're looking at lucerne on sandstone, we're looking at lucerne on clay, we're talking rape on sandstone, rape on clay, and pasture on clay. And all they did was their normal dose of superphosphate, which the Kiwis are crazy about. Whether it's good or not, it's debatable, but it does something. But the normal doses, and all they put was a cup, 1 cup, 250 grams of sodium molybdate with the superphosphate. Here's the yields without it, here's the yields with it, there's the increase. The smallest increase was 38%, the largest was 603% increase with 1 cup of sodium molybdate. And there's 350, there's 390, there's 78, smallest is the 38. How on earth is that happening? Really simple. These are broadacre nitrogen deficient crops, and you just gave the key to the door to release excess 5,000 truckloads of urea, some of that, to give, there's only nitrogen give you a 600% yield increase. There's nothing else. There's no known thing that can do that except nitrogen. You just unlock the nitrogen by putting the molybdenum in there. And 80% of you need to do that because that's the level of deficiency of molybdenum. Understand not to neglect that mineral.